this video, I'm going to be showing you how to approximate the linear correlation coefficient of a two-variable distribution from a word problem. Here's our word problem. An economist studies average daily sales of a frozen product as a function of its price increase over several years. Here are his data. And you can see that our table says sales price and then daily sales, and then it says sales price and daily sales again. This is just because it's all one table that I had to split in two and stack on top of each other so we could read it a little better. What we really need to know here is there a correlation between the sales price and the daily sales? If there is, we need to know if that's going to be a strong or weak correlation. So to answer this question, we're actually going to estimate the linear correlation coefficient by using the rectangle method. There are 3 steps to this method. The first is going to be to graph the data, and then we need to draw a rectangle around the data and measure its length and width. And finally, we need to use those measurements to calculate the linear correlation coefficient using the formula you see here. So R, which is the linear correlation coefficient, is approximately equal to plus or minus 1 minus the small side of the rectangle over the big side of the rectangle. For step 1, we want to graph the scatter plot. And before we go ahead and do that, I really need to focus on labeling the axes, which you've seen I've gone ahead and done here. My x-axis is the sales price, and the y-axis is the daily sales. Then I need to worry about how am I going to scale this. So on the x-axis, I'm going to make sure that everything's scaled by increments of 2. And because I'm using the rectangle method, it's actually easier if I can scale my y-axis in the same way. So I'm going to go ahead and do that. But to make sure that I get all the data points on there, since I don't really have anything that is below 24, I'm actually going to put a little break in my graph, which you can see right here. And then I'm going to start my scale at 24 and go up by increments of 2 from there. So now that everything's labeled and scaled, I'm ready to plot the points that you see above. That's what it looks like when you go ahead and do that. You'll notice that a lot of my data is like 7.99, 8.99. So the points are really landing, like you'll see this one here is at 8 and 40. So that's my 7.99 and 40 right there. It's very close to the value. So that's perfect. In order to go on to step 2, I need to start thinking about how to draw in the rectangle and measure the length and width. And in order to do that, I'm going to need the regression line, which you can see that I put in here in red. And from that, that's what I'm going to use to structure my rectangle around. To get the length of my rectangle, I want to make sure that I'm drawing lines that contain all the data. So the lines can either be on the data point. That's okay, but then otherwise, if it's not on the data point, all the data has to be inside those lines, and they're parallel to the regression line. The width, same thing. So I'm just going to cap my rectangle. And the important thing about the width is that I make sure that the 2 lines that represent the width are actually parallel to each other. Now, if I had an outlier in my data, so a piece of data that really didn't fit this trend, I wouldn't include it in the rectangle. Okay? You can see, though, that that's not the case in mine. So all my data fits nicely. I'm going to go ahead as is. So I need to now measure. And that just requires a ruler. There's nothing too big there. So when I measured the length of my rectangle, it came out to be 19.1, and this is in centimeters. And I need to use the same units on my width, and that width works out to be 3.7. It's also in centimeters. I'm now ready to go ahead and look at step 3, which is calculating the linear correlation coefficient using the formula that we discussed earlier. So remember, R is what I use to denote the linear correlation coefficient. My formula is right here, but now I actually have some values that I'm going to put in there. Before I go ahead and do that, though, I kind of have to pick between either plus or minus. And you can see that I've gone ahead and chosen the minus sign. And that is because looking at my data, I have clearly a descending regression line. Okay, so everything's going downward. So it is negative. After that, I just fill in the values that I've measured. So I have 1 minus 3.7 over 19.1, which gives me R being approximately equal to this. And I finally do my calculation to discover that R is approximately equal to negative 0.81. So we've calculated our linear correlation coefficient. We know that it's approximately negative 0.81, but we need to figure out whether this is a strong or weak correlation. So in order to do that, we're going to take a look at this chart here. And the negative, we know, talks about the direction that the data is trending, and we know that this is a decreasing trend in our data. So to talk about the strength of the correlation, we're really going to look at the absolute value of our linear correlation coefficient. So that's why you see the absolute value bars here in our data chart, or in our chart. And with a correlation of 0.81, we're looking at close to 0.75 and 0.87. Therefore, we can say that yes, there is a correlation. The linear correlation coefficient is negative 0.81, so it's moderately strong.